Okay, so let's get started for the second half. Um, in the first part, we introduced how we can predict the transition between different locations and cities. This is a much more challenging than predict the total inflow and outflow in each grid. So how this system works. Supposing we have four locations, R1, R2, R3, R4, and there are transition between them. And the figure associated with each edge means the number of crowds from one node to another node. We're trying to predict the transition like this. So we can further transfer them into a metric. For example, this is R1, R2, R4, and the transition between them can be modeled by a link between them. Then we can formulate them into a matrix, where each row stands for one region, and each entry means the inflow to the other four regions and the outflow to the other regions. So basically, it can be modeled as this matrix. You can see there are two people leaving R1 and entering R2. So this is 2. And there are one people leaving R1 and step into R4. So you can basically transfer the transition between regions into a matrix, where each row stands for one region, and the first 4 columns stand for the flow departing from region and entering into corresponding region. And the second 4 columns denotes the number of flow arriving at the region from other regions. Now, we can transfer them into this manner. There are 4 regions, R1 and R2, and each region has 8 channels because there are 4 income, 4 outcome, 4 income. So you can regard them as a tensor. 4 regions, each of them has 8 channels. So these are 8 channels. Then we can transfer this problem to the inflow-outflow prediction. But in the inflow-outflow prediction, we only have 2 channels, in and out, for each region. But now we have 8 channels to predict because there are 4 regions. So there are 4 by 2. I mean 8 regions in out to predict. Now we can apply the same model we just designed to model the temporal closeness, the pure information, the trend information. But before that, you have to do an encoding layer. This is encoding because the transition is very sparse. So we incorporate some graph embedding algorithm. So we don't design some specific encoding algorithm. We just use one full kinetic layer to do embedding. So after embedding, we can do the similar deep learning module. And once we have the component for prediction the transition between different locations, we can couple the prediction of transition with the prediction of in and outflow. So it's formulate a multitask deep learning framework. So you have one framework predicting the inflow outflow, and another one predicting the transition. And they share the common layer. So we can concatenate the latent layer of 2 frameworks and formulate another one. Okay, so it's called a bridge, concatenating bridge. Here, you can create a bridge. And also we define object function because the transition step into a region, the sum of transition step into a region should equals to the total inflow of the region. So in the equation, in the object function, you can define such kind of a multitask constraint. So because of the multitask, we can do prediction for inflow, outflow, and prediction of a transition more accurately. So this is a multitask, a deep learning framework. Okay, I just mentioned 2 cross-domain knowledge fusion methods, stage-based and feature-based, and deep learning is one type of them. Now, I will introduce more about semantic medium-based fusion, knowledge fusion. So why we call knowledge semantic medium-based? Because when we use deep learning algorithm, we don't care the semantic meaning of each type of feature. We just treat the deep learning as a black box, throw the data into the black box and do the fusion. But now in the following methods, we do care the semantic meaning of each type of data, and we also care about the semantic meaning of each type of feature and the relationship between each type of feature, between each pair of features. This is the first reason we call semantic meaning based. And the second reason is the 4 subcategories of method are derived from the way how people think of multiple data sets. That means when you are presented with multiple data sets, how can you feel the knowledge from them? I can only imagine the 4 ways. One is the multi-view. Second one is probabilistic dependence based one. Third one is similarity based one. The fourth one is transfer learning one. I will elaborate on each of them with some example. The first one is called multi-view based learning. So an object has different perspective. We can look at this project from different perspectives, but if you only look at them from one point of view, you have insufficient information describing the object. But if you have multiple views of information, by fusing the information from multiple views, you can have a deeper understanding of the object. So this is called multi-view learning based. Okay, I'll give you one example. Okay, air quality project, which is related to everyone here because you need to breathe. Okay, in China, this is a big issue. Just like many developing countries, air pollution is a big concern. Governments have deployed many air quality monitoring stations on the ground to inform people their ambient air quality information every hour. But such a air quality monitoring station is very expensive in terms of land use, resource for maintenance and deployment, also the money. It's very expensive. It's about 1 million per station, and you have to occupy a certain size, like a corner of this room. It's not that small, it's very big. So we only have very limited monitoring station deployed in a city. But in reality, the air quality changes over location tremendously. It's highly skewed in city. This is a replay of the real data, where you can see each icon stands for one air quality monitoring station, and the number associated with each icon means air quality index. The smaller the better, the bigger the worse. Green means very healthy, and the red means very unhealthy and hazardous. As you can see, even at the same moment, the air quality of 2 nearby location could be very different. You can see this one. They are very close to each other, but the reading are very different. It's not surprising to see this phenomenon, as air quality is impacted by multiple complex factors, like traffic flow, source of air pollution, the density of building in this area. All this information are different in different parts of the city. So they're highly nonlinear. You cannot do some linear interpolation. So what if there's no station built here? We cannot simply do some linear interpolation based on its nearest neighbors. How to solve this problem? We solve this problem by inferring real-time and fine-grained air quality throughout the entire city based on 2 parts of big data. The first part of the real-time means we do inference every hour. Fine-grained means we can infer a region with 1 kilometer by 1 kilometer square region throughout the entire city. The data is comprised of 2 parts. The first one is historic and real-time air quality data from existing stations. The second part of data is further comprised of 5 data sources: meteorological data, wind speed, temperature, humidity, structure, traffic data, and flow of people. I mean, human mobility data, number of people step into a location, and number of people departing from a location, and point of interest data. How many restaurants are there? Number of factory, and then the density of a building in this particular area, and also structure of road network data. The number of intersections, number of traffic lights, and number of highways, the length of highways. By using a machine learning model, we can build a mapping between the data we observe in a location and the air quality of the location. Later, by applying the model to other places, even if there's no station built, we can infer the air quality of that place based on data, because all the data are available in cities. This is a system, this is a publication, paper published at the KDD 2013 and finally deployed with Chinese Ministry of Environmental Protection in 2014. You can check the air quality of any location, even if there's no station built. And recently, we put together data from a cluster of cities that are near to each other. Because when there's a city gets some issues, the problems might not lie in the city itself. By using the information from a cluster of city, we can see when air quality tends from good to bad, which location becomes bad first, and then you can infer the propagation of air pollution and finally trace the source of pollution. So such kind of fine-grained information is very useful to inform governments in decision making, and also to inform people's trip planning. For example, where and when should we go jogging? So you cannot see the information of some station because they may be very far from your location. How we can solve this problem? We can try the system. We partition a city by uniform grades. We assume the air quality of a location is impacted by the data from its own grid and also its 8 neighboring grids. So the 9 grids formulated at the impacting region of each location. Then we can extract 5 categories of feature from the impacting region for each grid. For example, what's the meteorological data in this region, and how people move around, and what's POI feature around this in this particular region. After the extraction region, we can first formulate this problem as a multi-class classification problem. The prediction is a category of air quality. The air quality level, like good, unhealthy for sensitive group, or very unhealthy or hazardous. But we only have 35 stations in Beijing generating air quality label data every hour. But if we partition the city into 1 kilometer by 1 kilometer grids, there are over 2,000 grids to infer. So the label data is insufficient. So this is a label sparsity problem. We have to leverage knowledge from unlabeled data. So we come up with a co-training based semi-supervised learning program. Let me elaborate on why use co-training based method. So this figure illustrates the philosophy of the model, where each white circle denotes a station that has been built by government. We know the reading of air quality from these stations. And the blue circle means the air location we're going to predict. We have no idea about the air quality of this place. Each slice means the timestamp, 2 p.m., 3 p.m., 4 p.m. First, the air quality in one location has a temporal dependency, represented by the broken arrow, vertical arrow, because if the air quality of current hour is not good, the air quality of next hour tends to be not good either. Second, the air quality of different location may have some spatial correlation because air pollutants may be blown from one place to another places, represented by the red arrow. So in order to predict the air quality of a location, we need to simultaneously consider the temporal dependency of air quality in one location and the spatial correlation of air quality among different locations. So that's the reason why we use the co-training. They have 2 distinct views. One is a spatial view. That means we can predict the air quality based on its spatial neighborhood. We can also predict the air quality based on its own data, like a meteorological data, human mobility data in the location. So we have 2 dedicated classes classified corresponding to the 2 views. One is a spatial classified, taking into account the geographic data of different locations to model the spatial correlation of air quality between different locations. And the temporal classified, taking into account the traffic information meteorological data to model the air quality, the temporal dependency of air quality in this location. Then the 2 classifier has a mutually reinforcement learning process in a co-training framework. Okay. More specifically, the temporal classifier is based on a conditional random field. Supposing each node stands for the air quality state of 1 hour, which is invisible. We're going to predict the hidden state of the location in over a period of time. So this is for example, the 2 p.m., 3 p.m., 4 p.m. And what we can observe is a feature like meteorological feature, the traffic feature, and the time of day feature at each location, each time of stamp. So this is a conditional random field. It's a linear chain conditional random field. This is a on the shelf model. So spatial classify, we pair a location we're going to predict with other stations. For example, with 3 stations that are well available. We calculate the difference between their geographic features. For example, we can calculate the geographic distance between the location we're going to predict and the station. Also, we can calculate the distribution of their POI data and put the difference as input combined with the air quality of this station. And the output is the air quality of the location we're going to predict. This sounds like a nonlinear interpolation model, considering the geographic difference of different locations to do a nonlinear interpolation. But in order to generate more accurate results, we need to pair this location with multiple set of stations and calculate their difference and through the mental model and generate result. The training data, the model to training data comes from the station data. That means we pair one station with 3 set of stations, 3 stations, and train the model. And also we pair this station with another 3 stations until this model has been well trained. This is in order to learn the impact of different distance or impact of different geographic property to the model. Because when we choose a location, we don't really know where its nearest neighbor 3 locations, nearest neighboring location. You have to pair one location with multiple sets of stations. So if we pair them with 20 sets of stations, we will generate 20 predictions. For example, in the 20 predictions, there are 10 predictions saying good, and 5 predictions saying unhealthy. So the probability of being good air quality is 50%. So that's the reason why neural network will generate probability. Typically, neural network will not generate probability. But after we do multiple rounds of prediction, we can count the frequency of different categories. Then we get a probability across different categories of air quality. So in the prediction, we have a very limited label data represented by blue points. We use the limited label data to train the tool classify. Then we use the classify to infer the unlabeled data. If some instance can be confidently inferred, we can bring the instance back to the training data. For example, if we can infer the probability of one location to be good with a probability of 90%, we can bring this back. Then also we can do the similar way for the CF model, and we bring it back. Then we use the data to retrain the tool classify until the unlabeled data has been used out or the performance does not increase anymore. So this is kind of a semi-supervised learning model using unlabeled data to improve the prediction. So the reason why we use co-training framework has 2 reasons. One, from the computer science perspective, we have very limited data, labeled data. We need to leverage more unlabeled data. From the domain aspects, there are 2 distinct views from temporal space or from spatial space, and also corresponding to the reason why there is a pollution. The reason of pollution comes from three parts. One is local emission. Second one, global propagation. That means air pollution blow from other places. Third, some second chemistry reaction between the local emission and the global propagation. So the co-training perfectly model the local emission, global propagation, and the co-training framework actually corresponds to the second chemical reaction. So this model is motivated by both domain knowledge and data science knowledge. So once the model has been trained, we can use them to infer the unlabeled data. For example, we can extract a feature for each unlabeled data. we can predict them individually, and the output of each model is a probability across different categories. Then we choose one category that with the maximal production of the two predictions. So this is how the prediction part works for inference. This step, we infer the current situation of any location throughout the entire city. Now the next step is to prediction over the next couple of hours. So this is a system we deploy with the Chinese Ministry of Environmental Protection in stage 2 in 2016, last year. You can see the prediction of any location over the next 48 hours. So I emphasize it's a fine-grained prediction. Fine-grained means it's not saying it's going to be good or not tomorrow. It's not going to say Beijing is bad. I will tell you specifically in one university, let's say Tsinghua University, it's going to be 55 in next 6 hours, and Peking University is going to be 100 over next 12 hours. So it's both fine-grained in time space and the location space. And this makes this problem much more difficult than average mean prediction. And also there are some inflection points you need to predict. When there are some extreme winds comes and there are some downpouring rainstorms comes, the air quality may change tremendously, showing an inflection point. The inflection point is really rare. Probably you can observe one inflection point in over 100 days. And the minority is very difficult to predict, as we know. If we do machine learning, a model usually fit the majority of data. Even we sacrifice the prediction for the minority, we can also receive a very good performance in terms of accuracy or precision. But the inflection point is really, really important to inform government decision making. For example, there's true story. We probably heard APEC Blue. APEC Blue means in China, during the APEC conference, Asian Pacific conference, joined by many leaders of major countries, government has do a lot of things to control the air pollution. They suspend some factory, they shut down their do some traffic control that allows only half of vehicles to travel in a city to lower the air pollution below a given threshold. But at some moment, the air pollution increased to some extent. Then you have to make some decision. Whether should we shut down factory with a farther distance to Beijing, because all the factory around Beijing has already been shut down. If you're trying to lower the air pollution, you have to shut down the factory with a farther distance. Such kind of shutdown will cause a very, very big loss for the country, maybe billions of money per day. But if you know tomorrow is going to be an inflection point, the air quality will tends to be good tomorrow, then it's not necessary to shut down any factory anymore. And it's not necessary to do less traffic control anymore. So such kind of inflection point is very important, but very rare, and even more important than the stock market. You can say you catch one inflection point in stock market, you can retire, right? But if you can catch here, it's even more important. Okay. The service has been deployed over 300 cities in China, informing government decision making every day. And it's also a publication in the KDD 2015. So first step, we inform the current situation. Second step, we do prediction. And what's the accuracy for prediction? I'm not going into details because probably it's too technical. You can read the paper. In terms of the accuracy, in Beijing, it can achieve 75% accurate in the first 6 hours, and for the next 48 hours, about 50% accurate. You might think 50% accurate is not accurate enough, but it's pretty high. Because if you know the accuracy for weather forecast, then you will think this one is really high. So the accuracy for weather forecast over the next 24 hours is only 40%. You might not realize that. We have data. We have communicated with the the experts working in weather forecast, the accuracy is only 40% accurate for 24 hours weather forecast. And the weather forecast is the input of our model. And we can do 50% accurate over 48 hours. So you can see the magic of the model. And then you can see how tremendously the air quality changes over time. And the green, the black one is prediction, and the red one is the ground truth. You can see there are a lot of inflection point occurs. You have to create not really very many. So you have to capture the trend very accurately so that we can inform government decision making. Okay, you can read the paper. I will skip the details. Another one is probabilistic dependent graphing model. It's a probabilistic dependent method. Graphing model is some typical methodology that can be used. So we know the dependency between some data sets. We know A results in B and B results in C, or A and B both simultaneously affect C. So based on the dependency, we can connect different data sets and use graphing model to do inference. So this is another type of data knowledge fusion methodology. I'll give you one example. Here, we're trying to do a better urban planning by combining human mobility data and the point of interest data. The goal is trying to infer the function or the region of different functions throughout the entire city. For example, this is a function distribution of Beijing. Well, the red region means educational functions area, and bright area means commercial area. But as we know, the function of a region is not single. It's not unique. Maybe probably it's compound. It's a distribution of a different function. For example, even if we know there's a Tsinghua University and Peking University located in this place, does not mean every part of this place serves the educational function. You may also observe some residential area or some company located in this area. So the function of this region can be represented by a distribution of function across different categories. Like maybe 80% of the function is educational, and 10% is residential area, and 10% for commercial area. So the region with same color actually represents the region with a similar distribution of function. I just say they are educational area because I try to make this problem simple and easy to understand. In reality, their function is compound instead of single. On the other hand, if we give you a region, well, it's a kernel part of this function. For example, this figure shows the core area of commercial area in Beijing. The darker the color is, the high probability that this place could be a commercial area. So the research output two pieces of results. One is the distribution of function for each area. And second, given a function, we show the core area, the density area of this place, of this function, the kernel density of a function. So why do we do this research? The result can be used to calibrate urban planning. We typically do urban planning every 10 years, but after 5 years after urban planning, we might find the city is different from its original planning. There are a few reasons. Maybe the planning is not that reasonable, and people formulate some planning automatically based on their own needs. And second, maybe our government officials, for example, our mayor, has been replaced. They come up with a new strategy, so they change the land use of some places. So before the next planning, we have to know what the current city looks like. You have to know where's the commercial area. You have to know where's the residential area. And also it's important for location selection for some business. For example, if I want to open a supermarket, I need to consider its distance to residential area. But if you don't really know where's the residential area, how can you plan, select a location reasonably? or application of this of the research. And why do we care about two types of data sets? Why not just using POI data sets? Intuitively, point of interest data can reflect on the function of a location to some extent. For example, if we see there are Tsinghua and Peking University located in this area, we might think this may be a educational area. But if you look at the two restaurants, both of them are recorded as a Chinese restaurant in the database. But apparently, they indicate different function. This one may be built in some neighborhoods serving local people, but this one may be built in some commercial area or even tourist attraction to attracting people from around the city. So only using the point of interest data cannot really reveal the function of a region. And human mobility data can help differentiate between the POI of the same category. And also, human mobility data can help us identify the function of region. For example, if we observe the majority of people departing from the region in the morning around 8 a.m. and coming back to the region around 8 p.m., then we can imagine this could be a residential area, right? So that's the reason we need to combine human mobility data with point of interest data. So how can we combine them? We just do a mapping. We can imagine a region as a document. The function of region just like the topic of a document. And the distribution of POI in a region just like the keywords describing the document. And the human mobility just like the words in the document. Now if you know that, we can use the topic model. If you know topic model like LDA, the basic idea of LDA is trying to represent that document with a distribution of topic. And further, a topic is represented by a distribution of words. Give you one example. So, for example, this document is 80% about cats and 20% about dogs in terms of a topic. And regarding the topic of dogs, you might see some words about bones or dog foods, something. So if we know such kind of topic model, then we can do the mapping. Then we can, regarding a region as a document, and the function of region, just like the distribution of topic across of the document. Once you know this mapping, you can, through the point of interest data and the human mobility data, that's words. I'm not going to describe the model in detail, just know the insight. Then you can apply the model. What you only need to define is the number of topics, K. Once you define this model, this is an unsupervised learning model. So it will generate the results automatically. The result is a distribution for each region across different functions. So how to evaluate our method? Okay. We can compare the inference results of 2 consecutive years in Beijing and see the difference. We see if the difference makes sense. For example, the A area was recognized as an emerging commercial area, emerging residential area in Beijing in 2010, but later became a under construction area. This seems surprising because it's already an emerging residential area. Why it becomes a under construction area? So we found that this is true because the tallest building called Zhonggozhun is under construction in region A. So it changes the commuting pattern of people living here. Then our model captures the change accurately. Now it's truly an under construction area. And here B is the Qianmen Park, which was recognized as a nature park, indicated by green color, but later becomes the black color, means a commercial area. As we know, around the Olympic Game of Beijing in 2008, this area was rebuilt with hundreds of shops and a restaurant located. Now it is truly a commercial area. And also we can compare the results of Ongjing area against its land use planning. This region Wangjing is planned for residential area, and our prediction is almost yellow, means emerging residential area, which is true. But we also see some purple place, which indicates emerging commercial area. These places are not originally planned by government, but evolving itself. So we should let our urban planner know. It's not bad, but we should let them know there's already something there. You should not build another commercial area anymore because there's already there. So this is based on a graphic model to fuse knowledge from point of view data and human mobility data. The third category is called similarity-based data fusion. There are two representative algorithms. One is called Carper matrix factorization. Another called is context-aware tensor decomposition. So why they can be used to fusing information from different data sets? So a very simple example is collaborative filtering. So we know A and B are similar. When the information of B is missing, we can use the information of A to fill, right? So this is the basic idea of collaborative filtering. But what if we have multiple data sets, S1, S2, S3, describing one object? We can calculate similarity between each pair of data sets of the two objects. So once we have multiple similarity between each pair of data sets, we can reinforce the correlation between the two objects. And the reinforced correlation between the objects can enforce the similarity between the two data sets. Let me give you one example. So before step into this example, let me ask you two questions. The first question is, how many liters of gas has been consumed by vehicles in the past 1 hour in Halifax? How many liters of gas has been consumed by vehicles traveling in Halifax in the past 1 hour? Some people told me this question sounds like an interview question of Microsoft. I think the government don't have the ground truth because they don't know. If they know, we don't need to do the research. I don't know the answer if I don't do the research, but we can know the model, how to solve this problem. And the second question is, what's the volume on PM 2.5 that has been generated by these vehicles? This is very important to inform government decision making. So when they are trying to lower down air pollution by traffic control, they can think about the research. So this research was reported by. We presented the research in 2014 in KDD in New York City, and immediately we got an interview by United Nations because this cares about many cities, planning, traffic, energy, and the environment. So this is widely related to many cities. So what we can do here, we can infer the travel speed, traffic volume, gas consumption, and the pollution emission of vehicles throughout the entire city, on each and every road segment throughout the entire city in the past 10 minutes. Based on GPS trajectory generated by a sample of vehicles, combined with point of interest data and the road network data and meteorological data. So it's still data fusion application. So this is a publication. Let me show you a real system. This is a system that has been deployed in Guiyang. The data is streaming into our system every second. Then we can infer the traffic volume, not only travel speed, on each and every route segment. Probably you have get used to the green, yellow, red, which are travel speed. But here, they indicate traffic volume. It's not travel speed. Let me test you. If the traffic volume is high, whether the travel speed is high or slow, fast or slow. So typically, the first answer came to your mind is slow, but it's wrong. Let's say how to define traffic volume. Traffic volume means the number of vehicles traversing a given road segment in a given time interval, right? If the road segment gets congested, the number of vehicles that can traverse the road segment is very, very few, right? If you fully congested, then it's zero, right? So when the traffic volume is high, the travel speed must be high, and the density of the traffic should also be high. So through this story, I tell you, we don't really have a traffic volume map. We only have a travel speed map. You don't really know how many vehicles traversing a given road segment. You only know it's green, but it's not enough for urban planning, and it's not enough for estimating the gas consumption and the pollution emission. Traffic volume matters much more than travel speed. So further, we can infer the gas consumption or pollution emission like PM 2.5, carbon monoxide, and the nitrogen monoxide on each and every road segment in the past 10 minutes. We can do it in a real-time manner. We know the traffic emission on each road segment. Then we can correlate it, the emission data on each road segment with the data from the air quality monitoring station. By combining two parts of data, we can infer what's the percentage of PM 2.5 was generated by vehicles. Then we can answer government's question. So this is very useful information. And how this works? We have a three-step approach. The first step, we infer the travel speed on each and every road segment based on very limited trajectory data generated by a sample of vehicles, because I say we only have a sample of vehicles contributing data to our system. Here we use test cab data because they are always traveling on roads. Of course, you can use other trajectory data like Uber data, but anyway, we only have a sample of them, which is not enough. Given a time slot, we may have only a few vehicles transmitting their data to our system. But on other road segments, we don't have observation. But it does not mean there's no vehicles, right? So how to infer the travel speed of each and every road segment is a challenge. So here we propose a context-aware matrix factorization to infer the travel speed of each and every road segment. This is the first step. I will go to detail in later presentation. Okay. The second step is to infer the traffic volume on each and every road segment. Here we use a graph model to do a unsupervised learning because we don't really have ground truth of traffic volume on each road segment. We only have some loop detector on highways, but we don't have loop detector on other major roads or service roads. So that's the reason why I need to do inference. Previously, we only have an unsupervised learning model, but as I just mentioned, we could have some sensor data from a few road segments. Now, by combining the sensor data, loop detector sensor data, and the trajectory data of vehicles, we can do a semi-supervised learning model. But the publication of 2014 is only based on unsupervised learning model. So once we have travel speed and traffic volume, then we can infer the gas consumption and the pollution emission of vehicles on each road segment. So there are some equations we can borrow from environmental theory, which have been tested for many years. So our contribution lies in the first two parts. Now let's introduce how this works. This is a road network with some trajectory received recently. If we have a trajectory generated on the road segment, we can easily calculate the travel speed of the road segment. We can calculate distance between two consecutive points. We then divide it by this time interval. We can derive the travel speed, right? This is very simple. Now we can formulate a metric where each row stands for a time slot, like 2 p.m., 3 p.m., 4 p.m., or 2:30 to 40. Okay, and each column stands for one road segment. Each entry denotes the travel speed of vehicles on this road segment and at this time interval. This matrix is very sparse, definitely very sparse, as I just mentioned. We only have very limited vehicles contributing data to ours. And for example, in Beijing, there are over 100,000 route segments, and there are only 60,000 taxi cab, and the majority of taxi cab travel on major routes. So, given a time slot, let me say, given 20 minutes time slot, over 95% of route segments are absent of data. So I mean, we don't have taxi traversing on the 95% of route segments. So how to infer the missing value of this matrix is a challenge. So there's one simple technology called matrix factorization. You can factorize a sparse matrix with the production of two low-rank matrices. And by multiplying them together, you can recover the missing value in the origin matrix. But there it only have 5% entries. How can you infer the 95% missing value based on 5% data? That's very inaccurate. Now we have some solution. We accumulate the data received in past 3 months. I mean, trajectory data in past 3 months. We build a parallel matrix where the row and the column has a similar meaning with this one. This stands for one time slot. This stands for one column, one row segment. And then an entry in this matrix denotes the historical average of travel speed on this row segment and at this time interval. So this was derived from 3 months data. This matrix should be denser than this one, right? This is only based on recent data, probably recent 2 hours, 3 hours, and this based on 3 months data. If you don't have data today, probably you have data yesterday at the same moment. So this one is much more denser than this one, okay? And the difference between this one and this one denotes the difference of travel speed of current time against its common time, okay? And also we have built another matrix where each row stands for one row segment, and each column denotes one feature. The feature matches geographic feature. For example, the number of net lengths and travel speed constraint, or the distribution of POI around this terminal of this row segment. All this information describing the geographic property of the row segments. The assumption is, if 2 row segments have a similar structure of row network and with a similar distribution of POIs, could have a similar traffic patterns at the same moment. So this feature describes the geographic property of each row segment. Then we model the traffic condition of the entire city through a high level. For example, we can partition the city into 4x4, 16 grids, and we project the recently received data onto the grids and build another matrix. Where each time slot denotes this row stands for a time slot, and each column stands for a grid, and each entry denotes the number of vehicles traversing these grids in at a given time interval. So this metric describes the high-level situation of the entire city, because on some holidays, the traffic of the entire city maybe it's only half of the usual pattern, because not a lot of people will go on vacation or driving to other cities. So the traffic in the city is only half of the usual pattern. And also we throw the 3 months data into the matrix, into the high-level grids, and build a parallel matrix where the row and the column has a similar meaning, and the entry means the historical average. I mean, on average, in the past 3 months, the number of vehicles traveling in the grid. The difference between the two corresponding entries means the difference between current situation and its historical patterns. On holidays, the value may be the half of this one. So that's the corresponding relationship. Then we can factorize the 3 metrics together by minimizing this function. This is called context-aware matrix factorization. The first part is trying to minimize the decomposition error of y. The second part is trying to minimize the decomposition of x. The third one is minimizing the decomposition error of z. And this is a regularization. Why the tensor, the context-aware tensor decomposition can result a better performance than just using one matrix? From the semantic meanings perspective, there are three combinations. One, we combine temporal correlation with spatial correlation. Second, we combine fine-grained information with high-level information. Third, we combine real-time information with historical information, real-time with historical information. With the three combination, we can accumulate more knowledge and then we can result a better performance. This is from the perspective of semantic meaning. But from the algorithm level, we can see the three metrics share some dimension. For example, there's T dimension, there's R. These two metrics can be built with a dense representation based on other data source. So this is very dense metric. With a dense representation, we can get a very accurate decomposition of R and Z low-rank metric. With an accurate learning of R and T, we can multiply them and recover these metrics more accurately. So that's the reason why we can get a better prediction by combining multiple data sets and how they are correlated. Okay, and regarding the traffic volume, we're trying to infer the volume of taxi cab on the, we're trying to inform the volume of entire vehicles, not only taxi cab, on the route segment. This is what we're going to infer. It's invisible, so we use Greek notes to denote invisible information. And what's the factor affecting the traffic volume on the route segment? The first one is the type of location around this place. And the type of location is affected by the POI features and the road network features. And also the traffic volume on the road segment is influenced by the time of day and the weather condition. What we can observe is only the travel speed and the variance of the travel speed and the number of taxi cab on the road segment. So that's the reason why I said we cannot simply multiply a factor to the number of taxi cabs we observe on road segment to infer the number of entire flow of vehicles on the road segment. We have to use such kind of graphing model to do inference. And using a EM learning framework, we can use unsupervised learning method to infer the traffic volume on each and every road segment. This is a result of evaluation. We can evaluate the travel speed. We can evaluate the traffic volume, drop out some route segment with travel speed. Then we can recover the travel speed and use the dropout information as ground truth to evaluate the prediction. So you can say our performance is the best one. And regarding the traffic volume, it's very difficult to evaluate as we don't have ground truth. So we send many students taking some video clips on street side. Later they manually count the number of vehicles passing the road segments in a given every 5 minutes. Then we use our prediction model, we predict the number of vehicles. Now we can use the ground truth manually counted by students to measure our performance. Later we'll have a company do many videotaping at the street side. We cover over 10,000 road segments at different time interval. We spend a lot of money on evaluation. That's a lot of money. And the final our accurate model is very accurate. Now with a unsupervised learning method, we can achieve over 30% accurate. I mean, the error is less than 30%. So it's almost useful. And the efficiency is very important. I said you have to do the inference in a timely manner. For example, giving you the data of past 10 minutes, you have to return me the results in 1 minute. Otherwise, the result may be not very useful. You cannot say, wait 1 day, tomorrow I give you the results. That's not useful. So you have to generate the result very accurate, very efficiently. We have some methodology to make it more efficient by combining database methodology with machine learning methodologies. Okay, so this is a publication and deployed in Guiyang City. So every example I mentioned here has been really deployed and published. And most algorithm and the data sets has been available on my homepage. So next one is related to New York City. When I came to New York City in 2013, they told me, I imagine people living in the United States, in New York City, do not care about air quality, but they do care about air quality because the government put air quality sensors in Central Park, which might not really disclose the air quality of New York City. But this is out of my imagination. So they also care about air quality, but there's another thing that they also cares about is noise, urban noise in New York City. So this story is I came to New York City because CASP is the partner of Microsoft. Mayor Bloomberg founded the CASP in NYU, New York University. So when I came to the university CASP center, Mayor Bloomberg asked me if you can use your big data technology to help us tackle urban noise. New York City is a city full of noise, different kind of noise, traffic noise, pop music noise, under construction noise. So you'd better be careful if you try to stay in Manhattan. If you select a hotel with a bad location, probably you will be waken up during midnight because the truck collecting some rubbish. They will generate a lot of noise. So it's a very bad experience staying in hotel in Manhattan. Be careful. So I was thinking about how can we help solve this problem as a data scientist. First of all, we need to answer 3 questions for governments. First, where is noisy? Second, how noisy is it? Third, why it is noisy? If we can answer 3 questions, then government can do something. So if you can tell me where is noisy and also why it's noisy, we can do something. But if you cannot tell them why it's noisy, it's not useful. But the 3 questions are not easy to answer. Because first, okay, let's say this sound disappears in a few seconds, or even less than 1 second. That means sound changes over time very quickly, tremendously, and much faster than air quality. And the sound situation, noise situation in this room may be very different from the location that is only 50 meters away. So if you are trying to monitor the noise situation in a city, you have to deploy a sound sensor, in every 100 square meter region, or even a finer square meter region. If you count the size of New York City, then over 1 million sensors should be deployed in order to monitor the urban noise, which is infeasible. And we don't have the human resource to take care of these sensors. Second, even if you have deployed a sensor, you can monitor the sound level by dB, but you cannot tell people's feeling. How to define noise pollution? The noise pollution does not only depend on the sound level, but also people's tolerance to noise. And the people's tolerance to noise change over time. During daytime, for example, right now, I speak with this loudness. You might be acceptable to listen to my talk, but during the night, when you're going to sleep, I keep on giving this talk. Then you may treat my talk as a noise, right? So that means the noise with the same level of sound may be regarded as different level of noise pollution during different time of day. And the sensor data does not tell us people's feeling. Third, noise is a mixture of multiple sources. Like for example, the noise of one location may be comprised of truck noise, construction noise, and music noise. If you cannot tell government the composition of noise, government can do nothing. If you can tell them 30% or 80% of the noise come from here, not here comes from traffic, then you can build some noise barrier to block noise. Or if you can tell them during night, the noise comes from loud music, they can do bar control, to operation control. Then that's the reason why this is not an easy problem to solve. If it's an easy problem, I think New York City can solve this problem years ago. So I found this challenging problem, how to answer this 3 questions. But fortunately, I found another data set in New York City. It's called 311. You might heard about 911, which is for emergency call. 311 is a complaint platform. That means this platform allows people to complain something that you think is imperfect in city, but it's not urgent. And when you make a complaint, you can use a mobile phone app or make a phone call. So the location, category, and time has been recorded with each complaint. In the data, noise complaint is the 3rd biggest category. So you can regard this data as a cloud sensing data. Each individual person sense them being in the situation. By putting the data together, we can diagnose the noise situation around the city. More specifically, this is a visualization of the 311 data in New York City. The higher a bar is, the more complaint has been made in one location. And different color stands for different category of noise constraint, noise complaint. So we can imagine the location with more complaints call, then this place could be more noisy. And the distribution of calls across different categories may stand for the composition of noise in this location. For example, if we receive 100 calls in past 1 year, okay, and among the 100 calls, there are 50 calls about traffic noise, and 30 about construction, and 20 about music. Then the composition of noise could be traffic versus construction versus music, 5 versus 3 versus 2, right? So this seems to a very, very good data set, but this data set was called a rubbish data set in New York City because it's very sparse. As we can imagine, we cannot have people reporting noise situation every time, everywhere. In many cases, people are too busy or too lazy to make a phone call. Even they are disturbed by noise. So we cannot barely infer the noise situation based on this data. So that's the reason why they call this a rubbish data set. But later found if we can correlate the data set with other data sets, we can complement the data set. So we combine the 311 data with 3 other data sets, and neural network data, point of interest data, and check-in data from social media. Why the 3 data sets are related? It's very intuitive. So if there are many road segments and intersection, there are many traffic lights, then there could be highway traffic. And the probability of listening to some traffic noise is higher because people maybe has no patience to wait for traffic lights. And also if there are many POIs around this place, if you found many restaurants or pubs around these places, then you are more likely to hear some loud music noise. So it's correlated. So if you observe more people checking in some places, that means the volume of people, of crowds, is higher than other places. And the people is a source of noise. Without people, the city will be quiet, right? Okay, so the 3 things are correlated to the noise situation. By putting them together, we can infer the noise situation of each region over a long period of time. It's not necessary to do a real-time inference for noise, because the real-time noise is not useful. We try to diagnose the historical situation, the pattern, and the composition of each time interval. So let me show you a real system deployed in New York City. They deployed in Microsoft Azure. You can see the noise situation of each and every location. Well, a deep color means highway noise pollution. It's not measured by sound level. It's the noise pollution level of each location inferred by 311 data combined with our data sets. So you can check the noise situation at any location, and you can rank the top 5 location here. Once you click one location, you can say the composition of noise at a different time interval, because the noise composition may change over time. In the morning, maybe the traffic is a major issue. During the evening, maybe the music. And in terms of, we can also check the single category. Okay, I think according to a study, the first biggest source of noise in New York City is loud music and party. So that's the reason come from the people themselves. Okay, and no matter what day and holiday, noise or loud music noise is always the number one source. And according to the loud music and the party, where is the worst place? Columbia University. Columbia University is located in Manhattan, surrounded by many parks. And after finishing class, students have to go someplace. They go to parks, they have enjoying parties, so creating a lot of noise there. So in terms of under construction, where is the worst place? Wall Street. Because after 9/11, the two buildings crashed. They work during night, so there are no complaints there. So if we're going to compare Wall Street, Columbia University, and the Riverside Park from New York City, we can see they have a different situation and a different composition of noise. Then you can make different solution for them. In Riverside Park and the Columbia University, loud music is the number one big source. But in Wall Street, under construction noise is the number one. So if we can know the fine-grained noise composition in each location, a government can make some decision to tackle the challenges. And further, we can correlate the noise situation in a location with the healthcare condition of the people living in this location. We can correlate them because there are some studies telling us if people stay in noisy situation for a long time, your blood pressure will be impaired, and we will got some mental issue. Okay. Okay, this is our solution. We model the noise situation of 311 data which received in past 3 years in a tensor. Well, the first column stands a region. We partition each city by major roads, and each region is bounded by some major roads. The second dimension means the category of noise. For example, the music noise, the under construction noise. The third dimension means the time of day, 3 p.m., 4 p.m., 4 p.m. And each entry means the number of 311 calls that have been received in a particular region at a particular time slot, and for each particular category. The tensor is very sparse, as I just mentioned. We don't have people reporting noise situation every time, everywhere, and on each category. But if we can fill the missing value in the tensor, we know the noise situation at each location each time, and by normalize the noise complaint received in each location, we can generate the distribution of noise composition in each location. Then we can formulate other metrics. For example, we can put the geographic data, POI network data into a matrix, where each row means a region and each column means a feature, like number of restaurants in your location, number of intersections in your location, the length of highway in the location. The meaning is two locations with similar geographic condition could have similar noise situation. And also we put check-in data into another region, where each row stands for a time slot, and each column stands for a region, and the entry means the number of check-in in each region. So from the rows perspective, we can measure the similarity between two time slots based on human mobility pattern. For example, in the morning rush hour, in the evening rush hour, they could have similar noise situation because the mobility pattern of people are similar. And in terms of the two columns, we can measure the similarity between two regions based on people's commuting pattern, checking pattern. And also we can study the correlation between different type of noise report. So we can draw a circle distance for each 311 complaint we received and see how it correlated with other type of noise complaint. For example, sometimes when we observe loud talking complaint, probably we will receive a loud music complaint because they are correlated. Because when people participate in partying, they speak very loudly. Then we put the three metrics together. We do a context-aware tensor decomposition, which is very similar to the matrix factorization. This is the first part is minimize the decomposition of the tensor. The second one is minimize the decomposition of this one, and this one, and this is regularization. So more specifically, we can say this is the decomposition of the tensor. This is the decomposition of the matrix, and this is decomposition of the matrix Y, and this is a Laplacian. Because C is a square matrix, correlation matrix, so it's a Laplacian matrix to model the correlation here. By minimize this object function, we can fill the missing value in this tensor more accurately. So why we can do a better job? Because the three context matrices are not very sparse. They can be built based on other data source. So with the accurate decomposition of R and T, then we can multiply them together to recover the tensor. The shared component between the tensor and the matrix. And the other matrix can be built from rich data sets without missing values. So that's the reason why we can do a better job. Okay, this is an evaluation. We can drop out some location and recover. This is one type of method. But we do real-world study. We send our students to measure the noise situation in a different location using a noise meter. But as I said, what we infer is not sound level. So we cannot use this ground truth directly, but we can use the noise sound level to rank this location, and then use a rank as ground truth. Then we can use its noise situation and rank them based on 311 data, and then evaluate our solution based on DCG. So this is how we evaluate them based on real-world study. The last method is called transfer learning. So people have the capability to transfer the knowledge we learn from one domain to another domain. For example, learning to recognize a table helps to recognize a chair. Once we learn a green apple, we know a red apple, right? People have distinctly have this capability. So how can we use such kind of knowledge to urban planning? I'll give you one example. In many cities, so for example, in major cities, in New York, in Beijing, we may have rich data sets. We can do a lot of things, do traffic prediction, we do air quality prediction. But if we go to a new city or small city, where the infrastructure is not well built, or the data is just received recently, we don't have enough data, or we may miss some type of data. Can we do inference? Can we leverage the knowledge learned from the rich data generated in major city to improve the inference in some small city, a new city? If we can do that, we can transfer knowledge between different cities. This is very cool. When we do some smart city project, we usually get some cold start problem. We don't have data, so we stop there. But if we can transfer knowledge from major cities, then that's very good. If you can deploy the noise model in New York, then you can deploy everywhere. How we can transfer? What we can transfer, and what we cannot transfer. Apparently, we cannot directly transfer the model we train based on data from the source city to a target city directly. For example, the air quality model. We can train the model in Beijing, but we cannot grab the model of Beijing to predict the air quality of another city, like for example, Wuhan, because the air quality distribution of the two cities may be very different. So you cannot do that. And what if we grab the traffic data of Beijing and apply the data to other cities? It's impossible because the road network is different of the two cities, right? You cannot grab the traffic data of one city to another city. It seems that there's no data that we can transfer. So what we can transfer? First, the relationship between different type of data sets can be transferred. For example, when there is a traffic congestion, the air quality tends to be bad. Such kind of relationship may be universal, and it can be transferred between different cities. First. Second, even if the data sets itself cannot be transferred directly, but if we project the data into a latent space, then we can use them together. For example, traffic data of Beijing is very different from Wuhan, but if we transfer them into a latent space, we might observe in the morning, rush hour, even rush hour, they get contrasted. But during other time of day, it's very fast. So in the latent space, they share the similar representation. They can be used together. Okay, based on the two insights, we designed the following transfer learning algorithm for urban computing. First, let me use air quality project as example. So we can extract feature from different type of data sets. Then we can, for example, each row stands for one instance, and each column stands for one feature, and each block means one data set. And in the target domain, we may miss some data sets. Here we only have 3, and for some data it's very sparse. So we can also extract some feature which is incomplete. Now we can learn some dictionary based on the data of a rich city. The dictionary encodes the relationship between different type of data sets. First. Second, it can be used as a base to project the data from different sites into a latent space so that it can be used together. So for example, we can project the data set of different cities into a latent space through sparse coding. Once we project them into a sparse coding space, we can put them together to train a model. For example, train a multi-model transfer learning boost model, okay, and do final prediction. So the key point is how to do the graph dictionary learning and how to do the transfer that boost learning. Okay, let me focus on, let's start with graph learning. So in the graph learning algorithm, we first partition a city into some grids. For each grid, there are different type of data sets to use. For each type of data set, we can extract different type of feature. So here we use different shape, stands for different feature sets, extract from different data sets. So here we have, for example, there are 3 regions, so there are 3 feature sets. First, for the same type of data sets, we can build a connection between them based on similarity. So once their similarity exceeds the threshold, we build a connection between them. And also based on geographic distance, we can connect feature from different data sets. Now we can formulate a hypergraph with 2 types of links. One is a link between the same type of data sets. Another one is a link from different type of data sets. Then we can do a graph clustering with some requirement. The first, we require each cluster to have 4 types of data sets because we try to learn the relationship between different types of data sets. If one cluster only have 1 data set, how can we learn the relationship between them? Second, we require the label of air quality that equally distributed in different type of cluster because we try to learn the relationship. And the label in each cluster should be as consistent as possible. For example, when the travel speed is low, the air quality tends to be bad. If the label of air quality is very diverse, you cannot learn the relationship between them. Then after learning with the constraint, this is a submodular graph clustering algorithm. Now we can use some approximate clustering algorithm to achieve some clustering result. Then based on cluster, we can build a dictionary for each type of data set. Okay, with data, we can train, with dictionary, we can project the data from different space into latent space. Then we can use them together. Then we train a separate model with each type of data set alone. Then use the prediction of the individual model based on each individual data set. We can get a final prediction. Then we can measure the error of each prediction. And given the instance that cannot be accurately predicted in the target place, a higher weight. For example, you can use this equation. The higher the error is, the bigger the weight will be given to this instance, because beta is a value smaller than 1. Okay. So general idea is, if the instance is not accurately predicting the target base, we should pay more attention in the next round. But in the source domain, if the instance here, we can measure the instance of each prediction. So if the cluster cannot predict the instance very accurately, we should drop the weight of this cluster in the source domain. That's different. So with the tool update, we can gradually get a converged results. So there are more details in the paper. I will not go into more. Okay. So to summarize, we have methodology for cross-domain data fusion, 3 categories. The second category is further comprised of feature-based one plus concatenation, deep learning-based one. And the third category is further comprised of 4 subcategories: multi-view, probabilistic dependency-based one, and the similarity-based one, and the transfer learning-based one. The survey paper is published here. You can go to my homepage and get the slides for more details. I want to skip some slides, and I want to definitely present this one. Okay, because there are some questions raised during the break. We usually talk about data scientist and the data analyst. What's the difference between a data analyst and a data scientist? Because many companies want to hire data scientists. They publish many advertisements. So there's a big difference between data scientist, because a scientist, and the data analyst. Data analyst is a person who can be given a well-defined problem and a well-defined data set and a well-defined results. Then the guy knows how to use some tools. He runs the tools on the given data set, generate a given format of results. One example is when we, in a bank, if we receive many applications for credit cards, we need to define if we should issue a credit card or not for this applicant, based on the information the person has provided. For example, the age, the income, and even if you have a house. So this is a very well-defined problem. It's a binary classification problem. The result is yes or no, and the input is a feature of the users. And you can grab the historic data because the bank has already issued many credit cards for users. And then we can know if the user has repaid their car in time. So you can design whether we should issue a car yes or no. You have some label data and corresponding feature data. So you can train a binary classification like a decision tree. So when a new request comes, you can apply the model and solve the problem. So that's a problem solved by data analysis. So data is clear, problem is well defined. You know what the result looks like, yes or no. And you know the decision tree, you can run the tool. Data scientist is very different. I can share some experience, my real experience, because I collaborate with government a lot. I am responsible for Smart Xuhui in Shanghai. Okay, so when I came to Shanghai, the Xuhui government asked me one question. How to say that? Okay, they told me that there is a road in Xuhui district with many dirty road. They asked me, can you remove these dirts with your big data technology? This is a question that should be answered by data scientists. And another question raised by the Beijing government is, we moved some official departments of Beijing to another rural side of Beijing. So what's the impact to Beijing's economy, transportation, and the environment? This is the question that raised by government. And the data scientists should answer such kind of question. They don't tell me what's this question. Is it a classification problem, regression problem, or outlier detection problem? You don't know that. They don't even tell you what kind of data set you can use. You should know yourself what kind of data set you can use. Know no data sets, no problem definition, and they don't even know what's the output of the model. You just get rid of the dirt. So that's a problem you need to answer. And you are laughing. This is reality, and we feel lucky if people can raise questions. Typically, when we collaborate with governments, they don't really know what's the problem. When we ask her, what do you need? They usually ask me what you can provide. They don't really know what's the problem. So all the examples I present here, when proposed by us, by data scientists, rather than governments, they don't even know their requirement, that what's their demand. It's not. So if they can tell me their requirement, I feel very lucky. So, I mean, furthermore, a data scientist should find the problem yourself. If we approach data analysis as an undergraduate student who should be given a well-defined problem and well-defined results, then data scientists should be a PhD student who will graduate very soon. He should find the problem themselves and solve the problem themselves and ahead of their customers. So that's a data scientist. So more specifically, what the data scientist should be equipped with. First of all, he needs to understand. They need to understand the problem itself very well. It's not necessary for a data scientist to be a domain expert, but for example, for the air quality project, we need to know what factor will affect air quality. If you don't know that, how can you choose data set? And you need to also know what's the existing methodology that have been proposed in traditional domain. Why this technology is good or not good. Why their technology cannot solve this problem. It's very important. By learning from existing methodology, you can learn how to design your own model. You can learn how to choose the data set. By learning from their methodology, you can know why they cannot work out. Then you can communicate with them with their language. You can persuade them to switch to your model. Do not imagine they will switch to your model, even if your model's performance is better than them. According to my collaboration experience with domain experts, the really difficult thing is not our machine learning model. It's about first how to find the problem from the domain, understand the problem from the domain, and it's finally how to deploy your model with domain experts in the domain. The middle part is the easiest one. The first part and the last part much more difficult. So you have to understand the domain very well, learn from the domain, speaking with their language, and know what is good, what is not good. So give you one example. I major in computer science. Apparently, I'm a data scientist, but I have been teaching in environmental school in Tsinghua University for 3 years. Teaching their course for graduate students in Tsinghua University for environmental theory for this class. So until you reach that step, people believe you are on my side. You are not my competitor. You are not going here to destroy us. We are going to help them. Big data guys or AI guys, we are not going to replace traditional domain. We are trying to help them with our technology. Then you need to understand their domain knowledge very well. So that's the first point. And second, you need to have a deep understanding of the data. Not only the format of data, but also the insights implied by the data. For example, GPS trajectory of taxi cabs indicate not only the travel speed on route segment, but also human mobility pattern. Because for each trajectory, we know where people get on a taxi and get off taxi. With such kind of pick-up, drop-off information, we know how people move around the city from its origin to the destination. With such kind of mobility pattern, we can further infer the function of the region, and even the economy situation and the environmental situation of the region. If you can think that far, you can solve the problem of domain A with the data from domain B. Then you will not feel data is not enough. You will not feel we are lack of data. So in this big data era, we don't lack data anymore. What we lack is open mind. The mind is not open enough. If we know the problem, if we know the insight behind the data set, we can definitely grab enough and sufficient data from other domain. And third, we need to understand the diversity of model, not only machine learning model, but database model, visualization model, data match model, and data mining model. Because when you solve problem, you need to acknowledge from different perspectives. And finally, you need to understand the cloud, how to use the cloud. And even you have to know how to improve the cloud by adding something or building some new components on the cloud. So overall, a data scientist is a guy standing on the cloud, looking at the data, looking at the problem, thinking about data, and combining different type of tool and models, and solving model and deploying them on the cloud platform to generate fresh knowledge to solve domain problems. So that's data scientist. Standing on the cloud, looking at the problem, thinking of the data, combining different algorithms and models, deploying them on the cloud platform, generating domain problems. That's data scientist. Okay, so this guy is rich. Not very easy to develop. According to our experience, you must spend at least 7 to 10 years to train such a kind of data scientist. And I don't think we don't really need too many data scientists. With such a guy, without such a guy, even if you have different components, it's still a piece of our work. It's still a piece of components. It's not well combined, okay? So I'm trying to summarize my talk with 3 characters. Urban computing is huge and big, and today we spend about 3.5 hours to present urban computing. We know we have 4 layers from urban sensing, urban data management, urban data analytics, and service providing. And this is a real system we deploy for urban big data. But you only need to remember 3 characters after this talk. If there are someone come to you and ask what's urban computing, you tell them the 3 characters. First, our goal is using big data to solve big challenges in big cities. So that's 3B. Our solution is using data management, data mining, and machine learning. That's 3M. And our results is a win-win-win situation among people, city, and environment. That's 3W. In order to remember them more conveniently, it's 3BMW. That's urban computing. Thank you for your attention.